All right, so with this circuit here, again, we had the 9 volts. We had the 1500 ohm resistor, and I arbitrarily found out that, oh, this diode had 3000 ohms resistance, and the lamp here had 350 ohms resistance. Okay, so this is what type of circuit again? Series. How do you know that? It's that one path for electricity to flow, right? Should be piece of cake by now. In a series circuit, there's one thing that we know is unique compared to a parallel circuit. What's that one thing that we know about electricity in a series circuit? Chandler? Current's the same, right? So anywhere on this circuit, if I were to take my multimeter and measure it, I'd pull out a lead, take my multimeter, touch that, put the lead in, touch the other point, hook it back up. It gets the same answer no matter where I measured it, okay? And that's good because that helps us solve some other things here. All right, so first thing, our total voltage is pretty easy because it's given. So we know total voltage is 9 volts. Total current we don't know yet, but I do know that I have to take current. If I do Ohm's law, current is equal to voltage divided by resistance. So I know I have to take my total voltage and divide it by my total resistance, but I don't know that yet, okay? So let's figure out our total resistance. Just a matter of, in a series circuit, it's really easy. You just add them together. So my first one is 1500 ohms. My second one is 3000 ohms. And then my fourth one is 350 ohms. And I get a total here of what? Yeah, 4,850 ohms is my RT. Okay? Alright, so I can add that to my formula up top here. And I could take my 9 volts divided by 4,850, and I can get my current of 0.0018, and I'm going to carry a 6 amps. Or if you converted this, we move it over at 1, 2, 3 places, I get 1.86 milliamps. Okay. Again, same thing like we talked about before. If you do convert it to this, make sure that you remember when you apply it into a formula that you convert it back to amps, since that's our base unit there. Okay. All right, so we need to go down here and prove this Kirchoff's voltage law, right? Where the sum of the voltage drops equals our total voltage. All right, it's going to help to check our math to make sure things are going out right here. All right, so I'm going to look at my voltage drop at each component. Okay, and again, remember, voltage is nothing more than a measurement of pressure difference from one side of an element or one side of whatever that thing is you have hooked up to the other. Okay, so if I'm solving for voltage, it's current times resistance. My current, since it's the same everywhere, is this. It's the 0.00186. It's the same, so I have to use that number for all three. Okay. What is changing is the resistance. So for component 1, I have 1500 ohms. Component 2, I have 3000 ohms. And component 4, excuse me, I jumped ahead here. Component 3 is 350 ohms. All right. When I do the math here, I find out that for my first component here, I have approximately 2.79 volts. My second component, I have approximately 5.58 volts. And for the third one, I got about 0.651 volts. When I add this together, what should I get? 9 are pretty close, okay? I rounded on the current, so when I actually added these three together, I got 9.021. So because of my rounding, it's off by a little bit. But the sum of the voltage drops equals the total voltage. So this is actually V sub T, total voltage. Okay. Any questions on that? Usually the series one, piece of cake. Everybody's got it. It's when we switch to the parallel one that people start to get a little bit more worried. Okay. Luckily for you, next one up